After studying this module, you shall be able to know about the concept of partial and semi-partial correlation. Learn about the concept of multiple correlation and know about the application of IBM SPSS 20 to partial and multiple correlation. Partial, semi-partial and multiple correlation. The concept of bivariate linear correlation can be extended to situations where more than two variables are involved and relationships among them needs to be studied. While studying any two variables and understanding their relationship, one may encounter situations when a third variable influences the relationship and may show erroneous results. The dependence on the third variable by both the variables of interest may jeopardize the research findings. Thus, it becomes important to use statistical methods that may help in identification and control of these variables and their impact on the statistic of interest. The current module aims to study those correlational methods which aim to study the relationship among more than two variables which may be interdependent simultaneously, eliminating the effect of an undesirable variable. The partial, semi-partial and multiple correlation methods enable a researcher to study the relationship between any two variables among the numerous ones being studied by holding the effect of others as constant or partialing out their effect. Let me explain this by an example. I know that age affects a number of variables like height, weight, IQ, etc. So, if one wishes to study the relationship between any two variables that simultaneously are influenced by age, then results may not be true between those two variables only. It is important to partial out the effect of age and then study their independent relationship. Partial and multiple correlation concept. Many a times a researcher may find two variables to be correlated, but this occurs only under the effect of a third variable that enjoys correlation with both the original variables of interest. The covariance that this third variable shares with the other two and needs to be identified and isolated in order to know the real correlation between the two original variables of interest. The partial correlation coefficient proves useful in such instances. The semi-partial correlations also proceed on a similar logic, but here the effect of the third variable may be removed from just one of the related variables and not both. The partial correlation coefficients turn out to be high when the variables share positive relationships, but if the partialed out variable also share an equally high or higher correlation, then the partial correlation coefficient may be lesser. Of course, the converse of this statement is also true. The researcher should be careful while using partial correlation, as partialing controls only the linear effects of the covariates. Thus, the variables must be sharing a monotonic relationship and any non-monotonic relationship should be either avoided or it will corrupt the findings. Both partial and semi-partial correlation coefficients are integral parts of the multivariate analytical techniques. Partial correlation is especially useful in testing theories and exploratory researches. A partial correlation provides an index of whether two variables are linearly related. Say, score on the verbal section of the SAT and the college grade point average. If the effects of a third or more control variable, say high school grade point average, are removed from their relationship. A partial correlation is a type of Pearson's correlation coefficient that can range in the value of -1 to +1. A significant positive partial correlation implies that as the values on one variable increase, the values on the second variable also tend to increase, while holding constant the values of the controlled variable, the effect of which has been partialed out. Partial correlations are conducted in order to understand why two variables are correlated. In order to interpret a partial correlation between two variables, we will first need to know the size of the zero order, that is bivariate correlation between the two variables. Partial correlations assist in understanding regression. The simplest partial correlation involves only three variables: a predictor variable, a predicted variable and a control variable. Suppose, as in the previous problem, an admission officer is interested in the relationship between a student's score on the verbal section of the SAT, the predictor variable and the student's final grade point average while in the college, that is the predicted variable. However, suppose high school GPA, that is the grade point average, is correlated with both college GPA and the verbal SAT score. Would there still be a meaningful correlation between verbal SAT and the college GPA if we control the performance while in high school? Will the removal of a high school GPA lessen the relationship between verbal SAT and college GPA? Let us explain this concept using an example. Examination results are supposedly related to both practice of the syllabus and anxiety experienced during exams. If a researcher wishes to explore the relationship between examination results and any of the two other variables, then the effect of the third one would needs to be partialed out. The figure explains the logic behind the concept of partial correlation. The variance contributed by examination results, practice of syllabus and examination anxiety are shown as they contribute to the understanding of partial correlation. We find examination results, examination anxiety and the practice of syllabus depicted as rectangulars. We find that examination result and the practice of the syllabus have a common overlapping area which has been marked to show as the variance attributed to examination anxiety. The figure B shows the examination results and also the practice effect, the variance contributed by practice. So, the figure A and figure B both deal with two variables at a time. In figure A, we are just taking the two variables of examination results and examination anxiety, and the overlap area show the variance that is mutual to both variables. So, the figure B talks about the examination results and practice and the variance contributed by practice and exam results. Let us have a more comprehensive look now to the problem in the part C of the figure 1. We have combined all the three variables together as they occur in the research data. Now, the common area has the overlap area, that is of the examination results, examination anxiety and practice effect is the one that we need to weed out, because we may be interested in variance contributed by only exam anxiety or the variance contributed by only practice. But there is a third area that has been marked out here, which is the variance explained by both exam anxiety and practice. This area now poses a problem to the researcher when they may be interested only in relationship among exam results and practice or exam results and exam anxiety. The partial correlation tries to take care of this dilemma or problem of the researchers. The multiple correlation is a measure of how well a given variable can be predicted using a linear function of a set of other variables. It is measured by the square root of the coefficient of determination, but under the particular assumptions that an intercept is included and that the best possible linear predictors are used. Whereas the coefficient of determination is defined for more general cases, including those of non-linear prediction and those in which the predicted values have not been derived from a model fitting procedure. The coefficient of multiple correlation takes values between 0 and 1. A higher value indicates a better predictability of the dependent variable from the independent variables, with a value of 1 indicating that the predictions are exactly correct and a value of 0 indicating that no linear combination of the independent variables is a better predictor than is the fixed mean of the dependent variable. Like in the example discussed above, the correlation between examination results achieved and the examination results predicted from the two variables of practice of syllabus and examination anxiety, when these two variables are used in a regression equation, the multiple correlation enables us to know to what extent the variable of examination results be predicted effectively using the combined action of practice and anxiety. So, in multiple correlation, rather than partialing out the effect, we find out which particular variable out of the available ones is better able to correlate with our outcome variable or to be predicted variable, and then the effect of others can also be studied simultaneously. The R or the multiple correlation can be found to be high when the predictor variables share a high correlation with the predictors. Also, the value of R is never negative or more than the correlation of criterion with any of the variables. The multiple correlation coefficient turns out to be high when the predictors have poor correlation among themselves. Let us see how these values can be interpreted. When you have a value of 1 for R, then the interpretation would be a perfect linear relationship. A value of 0 for R would indicate no linear relationship, whereas the R values which are on the higher side, that is approximating 0.9 or near that, would mean a strong association between the predicted variable and the predictor variable. The 0.5 would mean a moderate association between the predictor and the predicted variable, whereas a weak association would be indicated if our R value hovers somewhere around 0.25. The partial and multiple correlation coefficients are useful in many situations. They are useful when more than two variables are part of the study and correlation between any two is to be established. When the effect of some variables is to be eliminated or controlled, or while establishing a multiple regression equation of two or more variables, predicting a criterion or other variable using regression equation. These correlations are also useful when the purpose is to know about the importance of weight of each member of all the variables in the regression equation in contributing to the final result or criteria. By weight, we can also mean the proportionate contribution. For the time being, we shall explore this word and its concept related more when we go into the details. The two correlations, that is the partial and multiple, are also useful when the research requires predicting a criterion with maximum efficiency. Along with the utilities, there are certain limitations in the use of partial and multiple correlation. The partial correlation coefficient turn out to be more valid when the data from which the bivariate zero order correlation are calculated is linear. The number of cases should be sufficiently large when there are number of variables in the cases of partial and multiple correlation. Otherwise, inflated measures of the coefficients may be obtained, which may jeopardize the study. The investigators should be careful about the variables being partialed out in partial correlation, as sometimes the relationships are not clearly defined and thus may become difficult to interpret. One of the major limitations to multiple correlation is that it is always positive. As the sampling errors accumulate, it results in an inflated coefficient. The calculation formula for partial and multiple correlation. The partial correlation coefficients formula in terms of n variables, where R 1, 2.34 ranging to n is correlation coefficient between variables 1 and 2. After the dot, we have those variables which have been partialed out. Like in this case, the R1 2.34 to n, the relationship is between 1 and 2, and the partialed out variables are 3, 4 till the variable n. So, the equation 1 gives us the R partial correlation R 12.34 till n, R 12.34 till n minus 1 minus R 1n.34 till n minus 1 into R 2n.34 till n minus 1, and this continues with as many variables, divided by square root of 1 minus R 21n.34 till n minus 1 into square root of 1 minus r square 2n.34 till n minus 1. The partial standard deviation sigma 12.34 till n denotes the standard deviation on which the other variable's effect has been controlled. The given formula shows it for n variable. Sigma 12.34 till n is equal to sigma 1 square root of multiplied with square root of 1 minus r square 12 into square root of 1 minus r square 13.2 into square root of 1 minus r square 14.23, and this goes on till the last variable, that is square root of 1 minus r square 1n.23 till n minus 1. The partial regression coefficients, that is small b, the partial regression coefficient in terms of partial coefficients of correlations and standard error of estimate for n number of variables can be calculated using the given formula. B 12.34 for n variables is equal to R 12.34 till n multiplied with the standard deviation of 12.34 till n upon the standard deviation of 2.134 till n. The multiple regression equation. The multiple regression equation for n number of variables helps in finding the relationship between a variable x1 and n number of variables. The regression coefficients b in the equation give the weighted contribution of each variable to determining x1 when the variance of other variables is controlled. x1 is equal to b 12.34 till n into x2 plus b 13.24 till n into x3 plus, and this goes on till the last variable, which is b 1n.23 till n minus 1 into xn plus k. The standard error of estimate given as sigma est x1 in the multiple regression equation. The equation 4 gives the predicted x from the multiple regression equation. The standard error of estimate gives the error magnitude of estimated scores rather than actual score. So, the standard error of estimated x values is equal to the standard error of 1.234 till n. The coefficient of multiple correlation, that is R. The multiple correlation coefficient is between a variable also known as the criterion and the other n-1 measured variable. Numerical application of partial and multiple correlation. A study involved 3 variables: examination results, practice of syllabus, and examination anxiety. It was conducted on a sample of 500 college students, and they showed the following results as in table. The investigator wishes to know how well he can predict examination results from the data gathered on practice and examination anxiety. The table shows the primary data matrix of variables: examination anxiety, examination results 1, practice 2, and examination anxiety in column 3 for a sample of 500 college students. The mean, the standard deviation, and the correlation between the variables 1, 2, 3 that is the linear correlations, are also shown in the data matrix. The matrix shows that the mean, standard deviation for the variables coded as 1, 2 and 3 and the correlation coefficients are also shown among the variables. As the aim is to predict variable 1, it is taken as the criterion and the other two variables, that is 2 and 3, are taken as the predictors. Let us apply the formula we discussed in the last section and decipher the problem. For computing the partial correlation, the first step is use the formula given in equation 1 and the following statistics can be calculated. R12.3 would mean that we are trying to establish the relationship, partial relationship between the variable 1 and 2 while partialing out the effect of the third variable, which in this case is the examination anxiety. So, 0.60 minus 0.35 into minus 0.35 divided by 0.94 into 0.94 gives us the value of partial correlation coefficient between variable 1 and 2 while partialing out the effect of the third variable is 0.81. So, the correlation coefficient between examination results and practice would be 0.81 when all 500 students have the same level of examination anxiety. A similar explanation can also be given to the other two partial correlation coefficient, that is the correlation coefficient between the variable 1 and 3 when the effect of the second one has been partialed out, it is obtained to be 0.72, and the correlation coefficient between the variables 2 and 3 when the effect of the first variable has been partialed out. In that case, the correlation coefficient turns out to be minus 0.72. Step 2 is compute partial ST. Using the formula given in equation 2, the partial sigma can be calculated. Sigma 1.23 is equal to 10 into 0.64 into 0.334 and it turns out to be 3.072. The variability contributed by examination results only when practice and anxiety are held constant. It is interesting to note that the variability has reduced considerably as the correlation among the variables are high. Similarly, the variability of 2 while the effect of first and third variable has been controlled and the variability for the third variable when the effect of first two variables has been controlled are also shown to be 4.78 and 3.38 respectively. Calculating the weighted B and regression equation. The partial regression coefficients B are calculated using the formula in equation 3 and B12.3 turns out to be 0.52 and B13.2 turns out to be 0.65. Thus, the regression equation is x predicted is equal to 0.52 x2 plus 0.65 x3 minus 66. The regression equation is useful in predicting the examination results of a student once his practice and anxiety scores are known. This, although is the most probable examination result as predicted by the regression equation and not the actual one. The standard error of estimate turns out to be 3.072. Multiple coefficient of correlation R turns out to be 0.95 on application of the numerical values in the desired equation as discussed in the previous section. The calculation of multiple coefficient of correlation was done using equation 6 and it has been found to be 0.95. So, for the data given in table, the R gives the correlation between examination results actually scored by the students and the predicted examination results using the regression equation we just formed. The multiple correlation coefficient would tell the researcher about the extent to which the examination results would be determined by the joint effect of practice and examination anxiety. Summary: the concept of bivariate linear correlation can be extended to situations where more than two variables are involved and relationships among them need to be studied. The current module aims to study those correlational methods which aim to study the relationship among more than two variables which may be interdependent, simultaneously eliminating the effect of the undesired variable. Partial correlation is used to measure the association of two continuous variables after controlling for the association of other variables. Conceptually, what is being done is to first calculate the variance in the dependent variable that can be explained or accounted for by all the control variables, and then the variance accounted for by the control variables is removed from the dependent variable. Finally, the degree of association is measured between the variance remaining in the dependent variable and the non-controlled variable. Multiple correlation looks at the association between one continuous variable, often called the dependent variable, with a group of two or more continuous variables, usually called predictors. One use for a multiple correlation is to find out if there is a relationship between an independent variable and a dependent variable after controlling for a subset of all other variables. In this sense, the multiple correlation or multiple regression is used as a more sophisticated method of exploring partial correlation. The partial, semi-partial and multiple correlation methods enable a researcher to study the relationship between any two variables among the numerous ones being studied by holding the effect of others as constant or partialing out their effect. The semi-partial or part correlation is similar to the partial correlation statistic. Like the partial correlation, it is a measure of the correlation between two variables that remains after controlling for the effects of one or more other predictor variables. The multiple correlation R is defined as the correlation obtained on a criterion X and the scores predicted in the criterion from the multiple regression equation. The research conditions under which the correlation coefficients would be useful are discussed in the text, and the limitations in the use of partial and multiple correlations are also enumerated. The formulae to be used in the process of calculation of partial and multiple correlation and forming multiple regression equation are listed. The steps involved in the calculation of partial and multiple correlation are depicted by taking a 3 variable example.